It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start.
Okay, let's unpack this. We often talk about the internet like it's this magical cloud that just, exists all around us, right? You open your laptop, you click a button, and boom, you're connected to the world. It feels instantaneous, almost ethereal.
It does.
But today, we are going to strip away that magic. We are getting our hands dirty. We're going beneath the floorboards, behind the drywall, and deep into the invisible traffic that actually makes modern life possible.
That's right. We tend to treat our home or office networks like a utility like water or electricity. You flip a switch and you just expect it to work.
Of course.
But unlike plumbing, where a pipe is just a pipe that carries water from point A to point B, a network is incredibly dynamic. It's not just a series of tubes. It's more like a nervous system. It carries instructions, memories, warnings, commands. And today, we're not just talking about how to use it. We're talking about how to design and build it, from the actual physical copper cables all the way up to the data packets zooming around at, well, near the speed of light.
I love that analogy of the nervous system. And honestly, looking at the stack of research we have for this deep dive, I feel like we're about to become surgeons.
Yeah, there's a lot here.
We've got practical installation guides from the B-Structured Technology Group. We have academic papers on network design from preprints.org, some really good hardware breakdowns from fs.com, and then some really heavy-duty forensic stuff from Varonis on packet analysis. It's a full stack.
It is a diverse mix, and that's what makes this topic so rich. We are going to cover the full spectrum. We'll start with the physical reality, literally drilling holes and crimping wires, and then move all the way to the logical layer.
The invisible layer.
The invisible layer, yeah, where we deal with IP addresses and VLANs. And finally, we'll put on our detective hats and look at how to secure and troubleshoot this beast once it's alive using tools like, Wireshark.
So the mission for this deep dive is pretty clear. We want to turn you, the listener, from a passive user who just reboots the router when Netflix buffers,
We've all been there.
into an active architect of your own connectivity. We want you to understand why it buffers, and more importantly, how to build a system that hopefully doesn't.
Exactly. Whether you are prepping for a tech certification, trying to wire up a new office, or you're just insanely curious about how your smart fridge talks to your phone, this all connects to the bigger picture of how we interact with information.
It stops being magic.
And it starts being engineering.
Okay, let's jump right into the physical layer then. The plumbing, as you called it. I was reading through the guide from B-Structured Technology Group, and the first thing that struck me was that you actually have to make a big choice before you even pick up a tool.
Yeah, a foundational choice.
You have to decide on the architecture. Wired, Wi-Fi, or a hybrid of the two. Now, in 2026, I feel like most people just assume Wi-Fi is everything, Everything's wireless.
And that is a common assumption, but it's a dangerous one if you care about performance or security. The guide makes a very, very strong case that while Wi-Fi is incredibly convenient, it is technically inferior to a wired connection in almost every metric that matters for serious work.
Okay, so we're talking about speed, obviously. That's the main one people think of.
Speed is the headline, yes. But it's more about the quality and the reliability of that speed. Wi-Fi is a shared medium. It's a radio wave. It's a conversation where everyone is shouting in the same room.
Right.
It has to contend with physical interference from walls, from metal pipes, filing cabinets, but also radio interference from your microwave oven, your neighbor's Wi-Fi, Bluetooth speakers, baby monitors.
All that stuff is just polluting the airways.
It's creating noise. And the B-Structured Guide notes that because of all this overhead and interference, most wireless networks actually run about half their projected theoretical speeds.
Half. That is a massive drop. If I buy a router that says 1,200 megabits per second on the box,
you'll be lucky to see 600 in the real world. And that's if you're standing right next to it. It drops off fast with distance and obstacles.
Wow.
It is. Whereas a wired connection using, an Ethernet cable, that's a dedicated private lane, it's full duplex, meaning it can send and receive data at the same time without any collisions. There's no one else shouting in that room.
So it's a direct phone call versus a crowded party.
Perfect analogy. But beyond speed, there is the security aspect, which is maybe even more important.
Right, because to hack a wired network, you have to be physically plugged into it.
Exactly. To intercept data on a wired network, an attacker physically needs to get into your building, find a network port in the wall, and plug in. Or, somehow tap the physical line.
Which is difficult.
It's very difficult. It's a high-effort attack. With Wi-Fi, your data is being broadcast omnidirectionally through the air. If your encryption isn't perfect or if you're using an older, weaker protocol, someone sitting in their car in the parking lot with a high-gain antenna can potentially capture your network traffic.
That's a sobering thought. Walls don't block radio waves perfectly, but they definitely don't block determined hackers.
Not at all. So for the architect listening, the recommendation isn't kill Wi-Fi, it's use it correctly. Use it for what it's good for.
Mobility.
Precisely. This brings us to the hybrid model, which the source calls the Goldilocks solution. It's the best of both worlds.
So what does that look like in practice?
You wire the things that stay put, your desktop PC, your network-attached storage, your server, your printers, your smart TVs, and definitely your game consoles if you care about latency.
Oh, absolutely.
Anything that doesn't move and needs a stable, fast connection gets a cable. What that does is it clears up the airwaves, it gets all those noisy, high-bandwidth devices off the Wi-Fi.
So the Wi-Fi is then freed up for the things that need it.
Your phone, your tablet, your laptop when you're moving around the house. It's about spectrum management. You're making the wireless environment cleaner and faster for the devices that truly depend on it.
Okay, so let's say we've committed to this. We're going to run some wires. The 10-step installation checklist from the source material was surprisingly gritty. It wasn't just plug in cable A to port B.
No, it's real construction work.
It started with planning, and one specific warning caught my eye, and you mentioned it already. Interference.
Ah, yes. The invisible enemy of network stability.
The guide says, and I'm quoting here, do not run network cables adjacent to power outlets or electrical lines. I think most people, myself included, would probably just zip tie them all together to make it look neat behind the wall. Why is that such a bad idea?
Because of physics. Basic electromagnetism. An alternating current flowing through a power cable generates a fluctuating magnetic field around it. It's a powerful 50 or 60 hertz hum. If you run a data cable parallel to that power line for any significant distance, say more than a few feet, that magnetic field induces a small electrical current in your data cable. It's called EMI, electromagnetic interference.
So the data cable essentially acts like an antenna, and it's picking up the hum from the power line.
Exactly. And you have to remember your network card at the other end is trying to listen for these very delicate, high-frequency digital signals, the ones and zeros. But it's being drowned out by this loud, low-frequency buzzing from the power line.
It's like trying to have a whispered conversation next to a running jet engine.
That's a perfect analogy. You just can't hear the important data over the noise. Now, Ethernet cables are designed to fight this. That's why they're called twisted pair.
Right, I've heard that term. What does the twisting actually do?
Inside the cable jacket, the 8 wires are grouped into 4 pairs, and each pair is twisted together at a specific rate. The physics here is really clever. By twisting the wires, any external noise, like EMI from a power line, hits both wires in the pair at almost the exact same time, but with opposite polarity.
Okay.
The receiving device at the end can then look at the 2 wires, identify the common signal, the noise, and mathematically subtract it, leaving only the original intended data signal. It's called common mode rejection.
That is brilliant. But that math has its limits, I assume?
It does. If the interference is too strong, like running right next to a main power trunk for 20 feet, the noise just completely overwhelms the cancellation mechanism. You get corrupted data, which leads to packet loss.
And packet loss means?
It means your connection drops randomly, your video call stutters every time the air conditioner kicks on, your file transfer fails halfway through, and it's a total nightmare to troubleshoot because the cable looks fine. The tester might even say it's connected.
So what's the rule of thumb?
The rule is to maintain separation. Keep your data cables at least 12 inches away from parallel power lines, and if you absolutely must cross them, do it at a 90-degree angle.
A perpendicular crossing.
Exactly. That minimizes the length of the cable that's exposed to the strongest part of the magnetic field. It's a small detail that saves you a world of pain later.
That is the kind of detail that will save someone a weekend of tearing their hair out. Now, speaking of the cable itself, let's talk about the wiggle room rule. The guide suggests measuring the distance, adding extra for the patch leads, and then adding another 10% buffer on top of that.
This is the measure twice, cut once rule applied to networking, and it is non-negotiable.
Why so strict? You can't just stretch it a little bit.
Laughs. No, you cannot stretch copper. And more importantly, as the source notes, you cannot effectively join or splice Ethernet cables in the middle of a run.
You can't just, twist them together like speaker wire with some electrical tape.
Please, please do not do that. I mean, physically you could, but you would completely destroy the delicate twist geometry we just talked about. You'd be creating a massive, unshielded point of failure and interference right in the middle of the run.
So it has to be one continuous piece of copper.
One continuous run from the central patch panel to the wall jack. No exceptions. If you are running a 50-foot cable through the ceiling and you come up 6 inches short, you are not splicing on an extra piece.
What do?
You pull that entire 50-foot run back out of the wall, you throw it in the trash, and you start over with a longer cable.
That hurts just thinking about it. So the lesson is buy the extra cable. It's cheaper than your time and sanity.
Absolutely. The 10% buffer is your best friend.
Okay, let's talk tools. We're not using a hammer and nails here. The guide specifically mentions a punch-down tool and a crimping tool. For anyone listening who might only have a screwdriver and a pair of pliers, let's clarify what these specialized tools actually do.
These are the essential tools of the trade for a wired network. Let's start with the crimping tool. It looks a bit like a beefy pair of pliers, but it has a special die in it.
And what's it for?
You use it when you are putting the plastic plug, the official name, is an RJ45 connector onto the end of a cable.
A little clear plastic thingy?
That's the one. The process is you strip the outer jacket of the wire, you untwist the little pairs, and you have to painstakingly line up the 8 tiny colored strands in the correct order.
There's a color code you have to follow.
A very specific color code, T568B, is the standard. You slide them into the little channels in the plastic plug, push it all the way in, and then you put the whole assembly into the crimping tool and squeeze hard.
And it does 2 things at once, right? It crushes the metal contacts down.
Right. It forces these tiny gold-plated teeth down through the insulation of the wires to make the electrical connection. And at the same time, it crimps a plastic strain relief tab to hold the cable securely in place so it doesn't pull out. It's a very satisfying click when it works.
Okay, so that's for the plugs. What about the punch-down tool? That sounds more aggressive. That's for the wall side.
Correct. When you install a network jack in the wall, you don't use a plug. The back of the socket has these little color-coded slots with metal contacts inside. They're called an insulation displacement connector, or IDC.
So you don't have to strip each of the 8 tiny wires.
No, thank goodness. You just lay the individual wires across the correct colored slots, and then you use the punch-down tool. It's a spring-loaded device. You place it over the wire and press down firmly.
And what happens?
You hear a loud thunk.
The tool does 2 things simultaneously. It forces the wire down into a little metal V-groove, which slices through the insulation to make contact, and a tiny blade on the side of the tool snips off the excess wire flush with the connector. That thunk is the sound of progress. A clean, solid connection.
It's a great sound.
But before we get to the thunking, the source had a massive, all-caps safety warning. Turn off the building power before cutting holes.
It seems obvious, but people get complacent. You're just cutting into drywall. What could go wrong?
A lot, apparently.
A lot. When you are sawing into a wall with a jab saw to mount a bracket for your network jack, you are flying blind. You have no idea what is behind that paint and plaster. There could be pipes, or worse, live electrical wiring.
And if you hit a live wire?
If you saw through a live 110 or 220-volt electrical wire, you aren't just going to damage your house's electrical system. You are creating an instantaneous arc flash. The tool can become electrified. You could be seriously injured or electrocuted. It happens more often than you'd think.
So the rule is?
Always, always go to your breaker panel and kill the breaker for the room you are working in before you cut, drill, or saw into any wall. No exceptions. Safety first, connectivity second.
A vital piece of advice. So let's fast forward. We've survived the installation, we've drilled the holes, we've avoided the power lines, we've run our beautiful continuous cables, we've pushed down our connections, we plug it all in. How do we know we didn't cross a wire somewhere in that color code?
You have to validate the physical layer. You can't just assume it works. The guide mentions using a network test tool, and this is critical. Even a cheap $10 tester from online is invaluable here.
What does it do?
It usually has 2 parts, a main unit and a remote unit. You plug the main unit into your newly installed wall jack, and you take the little remote unit to your central closet and plug it into the other end of that cable at the patch panel.
And then you turn it on.
You turn it on, and it sends a small voltage down each of the 8 wires in sequence, one by one.
And you're just looking for a specific pattern of lights?
You want to see the lights on both ends flash in perfect sequence. 1, 2, 3, 4, 5, 6, 7, 8. If they march in order on both the main unit and the remote, your cable is perfect.
And if they don't?
If you see something like 1243, it means you crossed a wire, you swapped the green and blue pairs, for example. The connection might still work, but it will be slow and unreliable.
What if a light just doesn't come on at all?
If light number 5 doesn't light up at all on either end, it means there's a break in that wire. Either your punch down wasn't deep enough and the wire isn't making contact, or your crimp on the other end is bad.
That instant feedback is crucial. It proves the road is built correctly before you ever try to drive a car on it.
Exactly. It validates that the physical layer is solid.
So that's part one. The physical layer. The messy, dusty, sometimes dangerous work is done. We have a nervous system of copper wires running through the walls. But right now, it's brainless. It's just metal.
Correct. We have built the highway system, but we haven't painted any lanes, we haven't put up any street signs, and none of the cars have license plates. It's just a bunch of pavement.
Which brings us perfectly to part two. The logical layer. This is where we start giving things names and addresses so they can actually talk to each other. We're talking about IP addressing.
The language of the network.
And I want to start with the huge generational shift the sources discuss. IPv4 versus IPv6.
This is the fundamental shift in how the internet identifies things. IPv4 is the system most of us know, even if we don't realize it. It's those numbers like 192.168.1.1. It's a 32-bit system.
And the math there is 2 to the power is 32.
Exactly, which gives you about 4.3 billion possible unique addresses. Back in the 1980s, the engineers who designed this thought, we will never, ever have 4 billion computers connected to the internet.
They were a little bit wrong about that.
Just a bit. Between phones, laptops, watches, cars, smart speakers, and now smart fridges, we officially ran out of new IPv4 addresses years ago. The well is dry.
So how did we survive this long? How is the internet still growing if we ran out of numbers?
We survived with a very clever but very complicated band-aid called NAT Network Address Translation.
Okay, what's that?
That's what your home router does. You get one real public IP address from your internet service provider. Just one. And your router creates a private little universe behind it using those 192.168 addresses. It hides all your home devices behind that single public address.
So it's like an office building where the whole building has one street address, 123 Main Street, and the receptionist has to look at the mail and decide which person in which office gets it.
That is the perfect analogy. The router is the receptionist. It's constantly translating between your one public address and your many private addresses. It works, but it's inefficient, and it breaks certain types of applications.
But IPv6 changes that game entirely.
Completely. IPv6 is a 138-bit system, and the difference in scale is just, it's hard to visualize. The source mentions it provides approximately 3.4 times 10 to the power of 38 addresses.
Which is a number so big it has a silly name, an undecillion or something.
Right. It's a meaningless number, basically. The common analogy is that it's enough to assign a unique IP address to every single grain of sand on every beach on Earth, and then do that for billions of other planets. We will not run out of IPv6 addresses.
And the implication isn't just more numbers. It changes how things work.
It fundamentally changes things because it means we can finally get rid of NAT. We don't need the receptionist anymore.
So every device gets its own public address, my phone, my watch, my light bulb.
Every single device can have its own globally unique public passport. This makes direct peer-to-peer communication much simpler and more efficient. The preprints.org paper highlights this as a major shift for things like jumbograms and overall network efficiency.
Jumbograms, that sounds interesting.
In IPv4, packets have a relatively small maximum size. If you send a big file, it has to be chopped up into thousands of tiny little envelopes. IPv6 supports these things called jumbograms, single packets that can be up to 4 billion bytes in size.
4 gigabytes in one packet.
Theoretically, yes. It's like moving your data from a fleet of bicycle couriers to a single freight train. It dramatically reduces the processing overhead on routers.
That's a huge leap in efficiency. But for our listener who is building their local network today, they're almost certainly still dealing with IPv4 internally, that classic 192.168 setup.
Yes, for now that's still the reality for most home and small business lands.
And here we hit a critical fork in the road for how those addresses are assigned, static versus dynamic addressing.
Right, and understanding the mechanism here is key to troubleshooting so many network problems. The default for most devices is dynamic.
The automatic setting in your network preferences.
Exactly, and it uses a protocol called DHCP, Dynamic Host Configuration Protocol.
What's happening under the hood when I connect my phone to Wi-Fi and it just works?
It's a very specific four-step dance called DORA.
DORA, D-O-R-A.
D-O-R-A. It stands for Discover, Offer, Request, Acknowledge.
Okay, walk me through it.
Imagine your phone connects to your Wi-Fi. It doesn't have an IP address yet. So the first thing it does is it shouts out a Discover packet. It literally broadcasts to the entire local network. Hello, is there a DHCP server out there? I need an address.
It's shouting into the dark, hoping someone answers.
It is. Then your router, which is acting as the DHCP server, hears this cry for help and sends a unicast offer back to the phone. It says, I hear you. I'm a DHCP server, and I can offer you the IP address 192.168.11110.
Does the phone just take it then?
Not yet. There could be multiple DHCP servers on a network, so it's a polite protocol. The phone receives the offer and sends back another broadcast packet or request saying, that's a great offer from that server, and I would like to formally request that IP address, please.
So it's telling everyone I'm taking this one.
Exactly. And finally, the router sends a final acknowledged packet, or ACK, says, confirmed, that address is yours. Here is your subnet mask, your gateway address, and your DNS servers. Oh, and by the way, this is a lease.
A lease time. So it's not permanent, it's a rental.
It is strictly a rental. The router might say, you can have this IP for 24 hours. After 12 hours, the phone will start trying to renew it. This is why it's dynamic. Next week, your phone might get a different number.
Which is perfectly fine for a phone or a laptop that comes and goes, but it's terrible for a server or a printer.
Terrible for anything you need to find reliably. Imagine if the post office changed the street address for your office building every single day. Nobody would be able to find you.
Right.
You don't want your printer's IP address changing because then your computers won't be able to find it to print. This is where you need static addressing.
So you bypass the whole DORA dance.
You completely ignore it. You go into the device's network settings manually and you type in the address. You say, you are 192.168.150, and you will always be that forever. You're ignoring the valet and parking in your own reserved, labeled spot.
Now, speaking of addressing problems, there is a specific dreaded number mentioned in the troubleshooting section of our sources that I think every listener needs to memorize.
Yes. I know the one you mean.
The 169.254 address, the APEA address.
APPA, Automatic Private IP Addressing. If you ever see an IP address on your computer that starts with 169.254, you are having a bad day.
Walk us through why. What does that number mean?
Okay, so go back to that DORA process. Your computer turns on, it connects to the network, and it shouts, discover, and then it waits and waits. And all it hears is silence.
No offer comes back.
No offer. Maybe the DHCP server on the router is turned off. Maybe the router is unplugged. Maybe your physical cable is broken. After a few seconds, the computer's operating system realizes it's been orphaned. It can't get an address.
So it just gives up.
It does something smarter. Instead of having no address at all, which would make it unable to communicate, it assigns itself a random address from the special 169.254 block.
It's like a cry for help.
It's a survival mechanism. It actually allows two computers that are plugged directly into each other with a single cable to top, which is neat. But if you see it on a normal, larger network, it is a giant red flag that means I cannot reach the DHCP server.
That is such a powerful diagnostic tool. So if I'm troubleshooting my mom's computer over the phone and I have her check her IP address and she reads me back a 169.254 number,
Stop everything else.
I immediately know.
Yep.
Stop checking the internet settings in Chrome. Stop worrying about DNS.
Yep.
The problem is between her computer and her router. Check the cable. Check if the little lights are blinking on the port. Check if the router is powered on. The device is screaming at you that the local line is dead.
Exactly. In one step, you've isolated the problem to the local physical link. It saves you so much time.
Okay, moving on to part 3 then. We have our physical road, we have our addresses. Now we need to manage the traffic. We need to be the traffic cops.
Yeah.
We are talking about switches and VLANs.
Now it gets fun.
And I want to start with the hardware because FS.com broke this down nicely. There is a huge difference between a cheap, unmanaged switch and a more expensive managed switch.
A world of difference. The $20 5-port switch you buy at a big box store is almost always unmanaged. It's a dumb box. It's a digital signal splitter. It takes data in on one port and it looks at the destination MC address and blasts it out to the correct destination port.
That's it.
That's it. It has no brain, no eyes, and no ears. It just moves traffic. It has no configuration interface. You just plug it in.
Which is fine for a really basic home setup.
Sure, if you just need to plug in your TV and your PlayStation, it's fine. But a managed switch, That's a computer in its own right. It has its own IP address, a web interface you can log into. It allows you to configure rules and policies for every single port.
And the most important and powerful rule is the VLAN.
Absolutely. Virtual local area networks. This is where we start slicing and dicing our physical network into multiple separate logical networks.
Okay, give me an analogy. How does that work?
Think of a VLAN as a parallel universe. Imagine you have one single physical office building that's your 24-port managed switch. Inside that building, you have 3 departments: sales, HR, and engineering. If you use a normal unmanaged switch, they're all in one gigantic open plan office. Everyone can see everyone else's desk. Everyone hears everyone else's shouting. That's a flat network.
It sounds like chaos.
In here,
And a massive security nightmare.
a huge security nightmare. Someone from sales could just walk over and look at the sensitive files on the HR server's screen. A guest who plugs into a conference room port is sitting on the same network as your critical engineering servers.
Right.
A VLAN allows you to build invisible, soundproof glass walls inside that switch. You can log into the switch and say, ports 1 through 8 are the sales universe, we'll call that VLAN 10. Ports 9 through 16 are the HR universe, VLAN 20. And 17 to 24 are engineering, VLAN 30.
So even though all those cables are plugged into the same metal box, a computer in the sales VLAN cannot talk to a computer in the HR VLAN.
They are completely, totally isolated at layer 2. The traffic from a sales computer literally cannot cross over to an HR computer through that switch. It's as if they were on 2 physically separate switches that aren't connected.
What's the mechanism? I want to get technical for a second.
Yeah.
The source mentions tagging, right?
Yeah.
The 802.1q standard.
Yes. This is how the magic happens. When an Ethernet frame, a packet of data comes from a user's computer and enters a port on the switch, say port 1, which is assigned to VLAN 10.
The sales VLAN.
Right. The switch's brain modifies that packet. It literally slices the digital envelope open and inserts a tiny 4-byte header a tag into it.
It stamps it.
It stamps it with the VLAN ID, so it injects a tag that says, I belong to VLAN 10. As that packet then travels through the switch or across special trunk links to other switches, that tag acts like a VIP pass at a concert.
Okay.
It says, I'm a VLAN 10 packet. If that packet tries to exit a port that belongs to VLAN 20, the HR VLAN, the switch looks at the tag and says, nope, wrong backstage area, access denied, and it simply drops the packet. It goes nowhere.
And then when the packet finally gets to its correct destination, say another computer in the sales VLAN,
Just before the switch sends the packet out the destination port, it performs one last action. It strips the tag off.
so the computer on the other end never even knows it was part of a VLAN.
Never has a clue. It just receives a standard Ethernet frame. All of the complexity and all of the security is handled entirely by the network infrastructure itself. It's incredibly powerful.
The Omnitron Systems source laid out some great use cases for this.
Yeah.
Security is the big one. Isolating that guest Wi-Fi so visitors can't browse your file server.
That's probably the #1 reason to implement VLANs. Your guest network should always be on its own isolated VLAN that can only go out to the internet and nowhere else on your internal network.
But they also mentioned performance,
Yeah.
something called broadcast domains.
Right. This gets a little more technical, but it's really important. Remember how the phone shouts with a broadcast to find a DHCP server? That's a broadcast. Lots of network protocols use broadcasts. In a large flat network, you might have hundreds of devices all constantly shouting things like, I'm here, where's the printer, who is 192.168.1.5.
Just constant chatter.
Constant background noise, and every single device on the network has to stop what it's doing for a microsecond to listen to every single broadcast and decide if it's relevant to them. If you have 500 devices in one big room, the noise is deafening. The network actually slows down just processing all that useless chatter.
So VLANs act like soundproofing for that chatter.
Exactly. A VLAN defines a broadcast domain. By putting those 500 devices into 5 separate VLANs of 100 devices each, you contain the shouting. The broadcast from a sales computer only gets heard by the other sales computers. It keeps the network quiet and much more efficient.
And then there's a special type of VLAN they mentioned, the voice VLAN. This sounds crucial for any business using VoIP phones.
This is a quality of life, or rather quality of call feature. Voice traffic is very small, but it's extremely sensitive to delay and packet loss.
What do you mean by sensitive?
Well, if you're downloading a huge 4K video file and your network drops a few packets here and there, the video might just buffer for a millisecond. You probably won't even notice. But if you drop packets during a phone call,
The voice turns robotic. It cuts out. You get that, can you hear me now? effect.
Exactly. It makes the call unusable. So what you do is you put all your IP phones on a dedicated voice VLAN, then you go into the switch and you enable QoS quality of service, and you give that voice VLAN the highest priority.
So you're telling the switch.
You're telling the switch if things get busy, if there's a traffic jam, the voice traffic gets to use the express lane, it cuts to the front of the line no matter what. It ensures your call stays crystal clear even if someone in the next cubicle is downloading the entire internet on the data VLAN.
So we've segmented our network. It's secure, it's organized, it's prioritized. Now, part 4, connectivity and application. How do we actually use this thing we've built? The Tech Mentor source had a great walkthrough on some basic fundamental tools, starting with the simplest one of all, ping.
The ping, the heartbeat of the internet. It's the first thing any network technician types when something is wrong. It uses a protocol called ICMP, and it's basically sonar for computers.
How does it work?
You send a tiny packet, an ICMP echo request, to a specific IP address. And if the device at that address is online and listening, it's obligated by the protocol to send an ICMP echo reply back. You get a little message saying, reply from, and how long it took in milliseconds.
Simple enough, but the error messages tell a story, don't they? The source differentiated between request timed out and destination unreachable. They're not the same thing.
Not at all. They mean very different things. Destination unreachable usually means a routing problem on your end. Your computer doesn't even know how to get to that address. It checks its routing table and says, I have no path to that network. It's like getting in your car to drive to a friend's house and realizing the bridge is out. You can't even start the journey.
And request timed out.
Request timed out means you found the road, you found the bridge, you drove all the way to your friend's house, you knocked on the door, and nobody answered. The packet got there, but it died waiting for a reply.
And what could cause that?
It could mean the device is turned off, or, and this is incredibly common, especially with Windows, a firewall on the destination machine blocked your knock. It saw the ping request come in and just silently ignored it.
Right. The Windows firewall is notorious for this by default.
It is. The source mentions a key troubleshooting step is to check the network discovery setting in Windows. By default, Windows assumes it's on a public network, like at a coffee shop, so it goes into stealth mode and ignores pings to stay hidden from other devices.
So if you're on your own trusted LAN that you just built, you have to go in and tell Windows, it's okay, this is a private network, turn on network discovery, answer the door when someone pings.
Exactly. It's a common gotcha that trips people up.
Okay, let's talk about another common use case, file sharing. This is something people struggle with constantly, just trying to get a file from laptop A to laptop B without resorting to a USB drive or emailing it to yourself.
It should be easy, and on a properly configured network it is, but permissions are what trip everyone up. The walkthrough in the source material clarifies that you need to configure 2 separate sets of permissions.
2 sets.
Yes. First, you have the share permissions. This is where you say this folder is shared on the network. And then you have the underlying NTFS file system permissions. Both have to allow access for it to work.
And within those, you have the crucial distinction, read versus read-write.
A critical distinction. Read permission means you can look at the files in this folder and you can copy them to your own computer. Read-write or full control means you can do anything. You can edit my files, you can save over them, or you can delete them entirely.
So you need to be very, very careful about giving write access to a folder.
Be extremely cautious. You don't want a guest on your network accidentally or intentionally wiping out your family photo archive because you gave everyone full control.
And finding the share once it's set up. The syntax is specific.
It is. In Windows, you open File Explorer, and in the address bar, you type // followed by the IP address or the host name of the other computer. So 192.168.1.5 or desktop PC.
And that tells the computer.
It tells the computer, don't look on my local hard drive. I want you to look across the network for a machine with this name or address.
It's like a portal to the other machine's hard drive. And once you're connected, you can map it as a drive letter, so it just shows up as your Z drive.
Exactly. It makes the network feel like a seamless part of your own computer. You can drag and drop files to it just like any other folder.
Okay, let's move to part 5.
Yeah.
This is the section I've been waiting for. The tech of work. We built the network, we're using it, but now we need to validate it and secure it, and we're going to get forensic here.
Validation is where the amateurs stop and the professionals begin. The NetBox Labs guide distinguishes between 3 types of validation: connectivity, performance, and security.
We've talked about connectivity with ping. What about security?
Security validation is where we get to play detective. It starts with knowing what's on your network in the first place. You can't secure what you don't know exists.
And for that, the Tech Mentor video showed a tool called Advanced IP Scanner. It described it as giving you a God view of your network.
It really is like that. It's a simple, free tool. You run this software on your computer. You tell it to scan your IP range like 192.168.1.1 to 254, and it just goes. It methodically knocks on every single digital door.
And what does it report back? What does it find?
Everything that answers. It comes back with a neat list,
Right.
IP address, the device's hostname if it has one, and its MAC address.
And the MAC address is the unique hardware serial number for the network card. Right.
Right. And what's really cool is that the first 6 characters of the MX address are a unique code assigned to the manufacturer. So the scanner can look that up and tell you, this is a Dell computer, this is an Apple iPhone, this is a Netgear switch, this is a Nest thermostat.
That is incredibly powerful, just being able to see that list.
It's your first and most important line of defense. You scan your home network, and you see your 2 laptops, your phone, your TV, and then you see a device labeled unknown manufacturer or Shenzhen Awesome Tech Company,
Right.
and you don't own any cheap smart bulbs.
You might have a problem.
You might have an intruder or a neighbor who guessed your Wi-Fi password. It immediately gives you a list of things to investigate.
But scanning just tells you who is there.
Yeah.
If we want to see what they're actually doing, we need to bring out the microscope. We need Wireshark.
Wireshark, the undisputed industry standard for network analysis. The Voronezh source calls it sniffing the wire, and that's exactly what it is.
How does it work? Because normally my computer's polite. It ignores traffic that isn't addressed to me.
Correct. Your network card, in its normal state, is polite. If a packet floats by on the wire that's addressed to your printer, your network card looks at it, says, "Not for me," and immediately drops it. It doesn't even bother the CPU with it.
So how does Wireshark see it?
Wireshark uses a special driver to switch your network card into promiscuous mode.
That sounds adventurous.
It just means it stops being polite. It forces the network card to capture and pass up to the operating system every single electrical pulse that hits it, regardless of the destination address. It becomes a network eavesdropper.
And when you first turn it on, I imagine it's just overwhelming, isn't it?
It's a fire hose of data. On a busy network, you'll see thousands of lines scrolling by per second. It's like looking at the code from the Matrix.
The interface has 3 main panes, right?
Yes. The top pane, pane 1, is the packet list. It's a summary. Packet number, time, source IP, destination IP, protocol, a little bit of info. It's the matrix code scrolling by.
And pane 2, the middle one.
The middle pane is where you dissect a single packet. You click on one packet in the list above, and this pane peels back the layers of the onion. It shows you the structure. Here is the raw Ethernet frame with the MSC addresses. Inside that is the IP header with the IP addresses. Inside that is the TCP or UDP header with the port numbers. You can see all the gears turning.
And pane 3, the bottom one, is the raw payload, the actual data.
Yes, it shows you the raw ones and zeros represented as hexadecimal code on the left and a best guess attempt at ASCII text on the right. If the data isn't encrypted, you can literally read it right there. Old insecure protocols like Telnet or FTP, you can see usernames and passwords in plain text.
The Voronezh source had a fascinating real-world case study on this, the Norman crypto miner. This is where the theory hits the concrete reality of cybersecurity.
This is a classic caught red-handed moment for malware. Researchers had a bunch of computers in an organization that were running really slow, but when they would open Task Manager to see what was using all the CPU,
The malware would hide.
the malware was smart. It was programmed to detect that Task Manager was opening, and it would immediately pause itself to hide its CPU usage. The moment they closed Task Manager, it would start up again.
That is diabolical. So the computer looks fine when you're looking, but the user swears it's sluggish the rest of the time.
Exactly. So they realized they couldn't trust what the computer was telling them about itself. The operating system was compromised. They had to trust the network.
So they fired up Wireshark.
They did. Now, just looking at the fire hose of packets won't show you a virus. They had to use filters, which is the most important skill in Wireshark.
Filters like, show me only traffic from this one computer.
That's a good start. But they got more specific. They thought, how does malware get its instructions? It has to phone home. So they filtered for DNS traffic.
DNS is the phone book of the internet.
Precisely. They filtered for DNS queries from one of the infected machines, and they immediately saw a pattern. These infected workstations were constantly, every 30 seconds, looking up the address for a strange-looking domain at a dynamic DNS provider, specifically DuckDNS.
And DuckDNS is a legitimate service, though.
It is. People use it for their home servers. But why would an accounting workstation be querying a random, nonsensical DuckDNS subdomain over and over again? That's a huge anomaly. It stood out like a sore thumb.
So they grabbed the IP address that the DNS query resolved to, and they created a new filter based on that.
Right. They set a filter like eip.addo equals that suspicious IP. They isolated the entire conversation between the infected PC and this strange command and control server.
And then they looked at the payload.
And then they looked at pane 3, the raw data. And because the malware authors were lazy or overconfident, they hadn't bothered to encrypt their command traffic.
No way. They could just read the instructions.
Clear as day. They saw simple text commands going back and forth. Things like, download this additional payload, start mining Monero using 50% CPU, stop mining. The command and control server was literally sending plain text instructions to the virus.
That is just incredible. The malware could hide from the operating system, it could hide from the antivirus software, but it could not hide the packets it was sending out to the internet.
The network never lies. If you send or receive data, it is on the wire. If you know how to look, you can see it.
No, we absolutely have to add the ethical warning here. The Spider-Man rule applies. With great power comes great responsibility.
Absolutely. The source is very, very clear on this. Only use packet sniffers on networks that you own or have explicit written permission to audit. Using Wireshark to capture traffic on your company's network without permission will get you fired. Using it at Starbucks to capture other people's passwords, emails, or banking data is a felony.
This is a powerful surveillance tool.
It is not a toy. Do not use this at Starbucks.
A very good warning. Use your powers for good. Let's look to the future to wrap this up. Part 6. We don't want to have to rebuild this network every 2 years. How do we future-proof it? The preprints.org paper talked about scalability and having a proper hierarchy.
Yes, it warns against what some people call the daisy chain of death.
What's that?
That's when you have a 24-port switch and you run out of ports. So you buy a cheap 8-port switch and you plug it into one of the ports on your first switch. Then you run out of ports on that one and you plug a third switch into the second one.
A switch plugged into a switch, plugged into a switch.
It's a performance and reliability nightmare. If that first switch in the chain fails, the other 2 switches and all the devices connected to them go offline. And the traffic from a computer at the very end of the chain has to make 3 hops just to get to the router. It creates bottlenecks.
So what's the right way to do it?
The paper recommends a proper hierarchical design, often called a core, distribution, and access model.
Break that down.
For a small to medium business, think of it like a tree. You have a core, a thick, high-speed trunk. This is your main powerful switch. Then you have your access switches, these are the branches, that are physically located out in the office areas where the users connect. Each access switch plugs directly into the core switch with a high-speed link.
A star topology, basically.
A star topology, exactly.
Look.
So if one branch, one access switch fails, it doesn't affect any of the other branches. The rest of the tree stands. And if you need more ports, because you're expanding, you just add another branch directly to the trunk. You don't grow a branch off a branch off a branch. It scales cleanly and horizontally.
And finally, the most boring, but arguably the most critical point in the entire process. Yeah. Documentation.
The bus factor.
Right. If the one person who knows everything gets hit by a bus,
does the entire company's network stop working? If you've built this complex, beautiful network with 10 different VLANs and a bunch of static IPs, and you didn't write any of it down, and then you leave the company, the next person who has to troubleshoot it is going to have to rip it all out and start from scratch.
Or, more likely, you, 6 months from now, will have completely forgotten why you set port 5 to the voice VLAN and why the printer is 192.168.0.53.
You will forget, I guarantee it. Use a proper tool like Netbox or even just a detailed spreadsheet. Record the source of truth.
Right.
What is each IP address assigned to? What is each VLAN for? What port on the patch panel corresponds to what jack in the wall?
Label your cables.
Label your cables, label your wall jacks. Future you will thank and present you immensely.
So to recap, we've covered a massive amount of ground here. We started by drilling holes in drywall, learning how to avoid those dangerous power lines, and understanding the physics of electromagnetic interference. We moved to the logical layer, giving our devices names with IP addresses, and learning the Dora dance of DHCP. We chucked our network into secure, isolated slices, using VLANs and 802.1q tagging.
Right.
We learned how to ping, how to share files, and finally, we turned into digital detectives with IP scanners and Wireshark to catch the invisible bad guys.
It's a journey from the physical to the logical to the analytical. And the big takeaway for me, really, is that a network isn't a set-it-and-forget-it appliance like a toaster. It's a living, breathing system.
Right.
It requires validation, it requires security patches for your switches and routers, and it requires constant monitoring.
And as we wrap up, I want to leave the listener with a final provocative thought based on our research into the Internet of Things, or IoT. This really connects back to everything we just discussed.
It really does. Your home network is no longer just for your computer and your phone. It's filling up with smart devices, webcams, smart locks, connected refrigerators, thermostats, light bulbs.
And these devices are often made by the lowest bidder. They rarely, if ever, get security updates, and they're all sitting on the same flat network.
And thanks to the push for IPv6, they might eventually all have their own public, globally reachable addresses. If you are not using the VLAN techniques we talked about to isolate your cheap, insecure smart fridge from the laptop where you do your online banking,
You have a potential bridge for attackers.
a huge one. If that fridge gets compromised, just like the workstations in the Norman crypto miner case, it can then be used as a launchpad to attack your laptop and your file server from the inside of your network, bypassing your main firewall entirely.
So the question is, who is listening to your traffic?
That is the question you need to be asking.
So the challenge for you, for our listeners, download a legal network scanner like Advanced IP Scanner. Or if you're feeling brave, download Wireshark and just watch. Just open it up on your own network. Look at the invisible traffic that is swirling around you right now.
See the invisible. You might be very surprised by what or who is talking on your network when you're not looking.
On that note, thanks for diving deep with us. Start building that nervous system and build it right.
Happy networking.